In this fourth video in this series, we're going to look at solving exponential and logarithmic equations. However, I need to lay down the foundation just in case you haven't covered this yet. But I'm assuming that if you're looking at this, you've already covered the main concepts, which are exponential functions and logarithmic functions. But let me go through the definitions here. An exponential function has the form y equal f of x, which is equal to b of x. Okay, so y or f of x equal b to the x power, and the conditions are that b has to be positive, b cannot equal to 1, and x is any real number. Now you can see why b cannot be 1, because if b is 1, then 1 to any power is always 1. So all we're going to have is y equal to 1, which is a horizontal line, okay, passing through the point 0, 1. So that's why we have the restriction that b has to be positive. And of course, we don't want b to be negative, because then if we have a negative number taken to say a fraction of power like 1/2 or 1/4, then we're going to have an imaginary value. Okay, so you want to avoid those. So that's why we have these conditions. So typically an exponential in general is just some base, say 2, taken to some power. Okay, so let's say 3. That would give us 8. Or say 5 taken to some negative power. This would be 1 over 5 squared, which would be 1 over 25. Okay, so that's what we think of an exponential, some base taken to a power. An exponential function, more restrictions. Like I said, the b has to be positive, and the b cannot be 1. One property of exponentials that I want to, again, make sure you know, because we'll use this in the equations that we're going to look at. If b is a base, again, with the conditions here, that it has to be positive and not equal to 1. If b to the x is equal to b to the y, it has to be true that x is equal to y. Okay. Again, it's not going to work if it's a 1, because you can say 1 to the 20th power is the same thing as 1 to the 30th power. But 20 does not equal to 30. Okay. So that's why we impose the condition that b cannot be 1. Okay. The next one is the definition of a log. Now, the exponential function are studied together with the log function, because these two functions are related. They're actually inverse functions of each other. So again, that means that if you take any point in one of them, any ordered pair, just in general, and I'm just going to make up variables here, x, y. It could be 2, 3. It could be the point 2, 3 or whatever, 1, 0, 0, 1. You take any ordered pair in one of them, and then you reverse the ordered pairs. Say instead of x, y, you have y, x. Then that would be in the graph of the other one. So in other words, if we take a point in the exponential and reverse the ordered pairs, then that's going to be in the corresponding log associated with that exponential, and vice versa. Okay, so just a little details concerning those. And the definition of a log, again, if x is positive, b is positive, so this base b right here is going to be pretty much the same as this one over here. Okay, so if x is positive, b is positive, again, b does not equal to 1, then we write y equal log of x to base b. So in other words, y is the logarithm. Okay, y is the logarithm of the number x taken to base b. So y equal log x to base b means that y is the exponent. So notice, y equal log x to base b if and only if x is equal to b to the y. Okay, so basically what this log expression here is saying is that y is the exponent that you have to take the space b to get the x. So this log expression right here is referred to as the logarithmic form. Okay, LF I have here, logarithmic form. And the second one, x equal b to the y, is equal to the, or is said to be the exponential form. Okay, exponential form. So just let me write it this way. So as an example, then I can say the log of 8 to base 2 equals, okay, so this would mean, this would be what exponent do I have to take this base 2 to get 8? Well, it would have to be 3, all right? Since 8 is equal to 2 to the third. Okay, so this is your logarithmic form, and this is the exponential form. So if you're given this, it means this, or if you're given this, it means this. You can go either way. Okay, sometimes they give you the log form and tell you to write it in exponential form. Sometimes they give you the exponential form, tell you to write it in logarithmic form. Okay. Okay, so again, as I mentioned, you can think of a logarithm and as an exponent. A logarithm is an exponent. So one note here, if you see log of x with no base indicated, that means the base is understood to be 10. Okay, so you don't have to put it in if it's the base is 10. It's understood. Log x with no base means log of x to base 10. Now if you see ln of x, again with no base, ln of x with no base, that's understood to be what is called the natural log function. Natural log function, and the base is understood to be e. So ln of x is the same thing as log of x to base e, where e is approximately 2.72 to two places, 2.72. Okay. Okay, so there you have some examples. And we will get into some very basic equations in this video, but the more complex equations will be coming up in the next video. Okay, here I basically want to lay the foundation, the definitions and so forth, properties that you'll need in order to solve the upcoming equations coming up in the next video. Okay, so here's some examples again. So just a basic exponential, 8 to the 2/3 power is equal to what? 8 to the 2/3 power is equal to what? Okay, a couple of ways to do this. Let me just set it up this way and say 8 is the same thing as 2 to the 3, or 2 to the third. And then the exponent is 2/3. And then again, your basic laws of exponents, those I expect you to know, or you should know. Power to a power here, you multiply the exponents. Okay, so 3 times 2/3, the 3's cancel out, you get 2 to the second. Okay, so that's going to give you 4. Okay, and let me just remind you again, in case you don't know this, if you have say some number x to the some fraction of power, some m over n, assuming everything is defined here, then this is the same thing as the nth root of x to the m, which is also the same thing as the nth root of x taken to the m power. Okay, so this is one way to do the problem, is using basic properties of exponents, and I got the answer to be 4. This tells me that if you have some base taken to a fraction of power, take the root of the base. That is, in this case, since the denominator is 3, I would take the cube root of 8, and that would be 2. and then I would take it to this power. So in other words, I'm using this right here. Okay, so I would take the cube root of 8, I got 2, and then take it to the power associated with the numerator, which is 2. So that would give me 2 squared. Cube root of 8 is 2, and then you square it, you get the 4. Okay, now if I use this one right here, then that would mean I would take the cube root of 8 squared. Okay, 8 squared is 64. And then what is the cube root of 64? Okay, what base to the third power gives me 64? Well, it's 4, right? 4 times 4 times 4 is 64. 3 factors of 4 is 64. So this is 4. Okay. So just some basic examples dealing with exponentials. Okay. So let's clear this. And again, remind you that in these videos, if I'm going too fast, just go ahead and stop the video and look at what I've done, rewind it, and so forth. So let me clear this. Okay, the next one is a very basic exponential equation. Solve for x if 4 to the x is equal to 32. And for this one here, again, there's more than one way to solve the problem, but I'm going to use the properties and definitions from this video here. And in particular, I'm going to use this property right here of exponentials. B to the x is equal to b to the y. Then it must be true that x is equal to y. Okay, so in other words, if you can get the base the same on both sides, then the exponents have to equal. They have to be equal. Okay, so let's go back to this one. So this is what I'm going to do. I'm going to say 4 to the x equal to 32. Obviously, here I don't have the same base, right? So let me write this with the same base. And do it this way. So I'm going to say 2 is the same thing as 2 squared. And that's taken to the x power. Okay. And I'm going to say 32 is the same thing as 2 to the 5th. Okay, power to a power, multiply the exponents. So the left side can be written as 2 to the 2x power. And the right side, of course, I leave it as 2 to the 5th. Okay, so now you see I have the base the same on both sides. So if the base is the same, the exponents have to be equal. These have to be the same number. So 2x should equal to 5. Divide through by 5. Divide through by 2. Both sides by 2. I get x is equal to 5 halves. And you can check it out because 4 to the 5 halves power is supposed to be 32. So check it based on the property I just gave you a while ago. I could take the square root of 4 is 2. And then I would take it to the 5th power. 2 to the 5th is 32. So it checks out. Okay. Let's do this. Now the next one, log of 27 to base 3 is equal to what number? Okay, so if you look at the definition of log, I want the exponent that you have to take this 3 to get 27. That's just using the definition of log. Well, that's going to be 3, right? Because three to the third is equal to 27. or 27 is equal to 3 to the third, same thing. Okay. The next one, number 4, write in write in exponential form. Write in exponential form. Okay. Well, again, in exponential form, if you look at the definition, it's just this expression here. The x has to equal to whatever the base is, taken to the power. Okay. So this, whatever is right here, where the x is, in this case it's x, has to equal to whatever the base is taken to this power over here. Okay, so if you look at the definition right here, y equal log x of base b is the same thing as, let me clear this, x then has to equal to this base taken to that power. X has to be b to the y. Okay, same thing we did. Okay, number 5, we have log to base 2 of the cube root of 2. Well, okay, what is this equal to? Okay, now if you can't see what the answer is to this, you can rewrite it this way. This is base 2, and then the cube root of 2 can be written as 2 to the 1/3. If that were a square root, that would be 2 to the 1/2, right? Fifth root, 2 to the 1/5, and so forth. So now this is saying, okay, I want the log of 2 to the 1/3 to base 2. So that's basically asking 2 to what power gives me 2 to the 1/3. Well, it should be clear that it's 1/3. Okay, so in other words, if these two bases are the same, right there, these two are the same, then the answer is going to be whatever this is, whatever power this is. If it's just a 2, well, the exponent is understood to be 1. So the log of 2 to base 2 would be 1, because 2 to the 1 is 2. Okay. Cancel this. Okay. Now the next one is a logarithmic equation. Very basic. Okay. Solve for x if log of x minus 5 is equal to 2. Remember, the base is not indicated, it's base 10. So normally if you have a very basic log equation like this, a single log, we just go directly to the definition. So by the definition, in this case, it's not an x. The expression here is an x minus 5. So x minus 5 should equal to whatever the base is. In this case, it's understood to be 10. Taken to whatever this number is. That's the logarithm of the exponent. So this would be 2. Okay. So this would be x then minus 5 has to equal to 10 squared is 100. Okay. Add 5 to both sides, and you get x is equal to 105. Okay. And that's your answer. And so you can check it out here, because if you put 105 where the x is, that'd be 105 minus 105. This would be 100. And the log of 100 to base 10 does equal to 2, because 10 to the second is 100. Okay, that's one way. It's just a quick check. Okay, clear this. Okay, in the next one, then we're going to look at properties of logarithms. Again, hopefully you already know this. So if you do, then you can just wait for the next video, where I'll get into more detail in solving exponential and log equations. But these are prerequisites for what we'll be doing with the solutions of the equations. We need these properties. Okay, so again, in these statements that I have here, these properties, it's going to be understood that wherever you see an m or an n or a b, those are going to be positive numbers. Okay, understood to be positive numbers. Okay, the base, like before, cannot equal to 1. Has to be positive, not equal to 1. R, where it appears, will be a real number. Okay, so let's just go through these real quick. Some of these I've kind of already mentioned. The log of 1 to base b equals to 0. Well, that should be clear because b to the 0 is 1. That's just your definition of log. B to the 0 is 1. Okay. The next one should be clear, I hope. The log of b to base b, the log of b to base b should be clear that that's equal to 1 because remember the exponent here is understood to be 1 here. So I'm asking b to what power gives me b to the 1 power? Well, it's going to be 1. Okay, that's clear. Now the next one might not be that clear, but this is saying if you have a base b and then you have an exponent and to a log power and the base of the log is b, then the answer is going to be whatever this is here. Okay, so this one not done as clear, but let's write it. Oh man, let me keep changes this. Okay, so let's suppose we want to show why it's equal to that. Okay, so let's say b to log. Okay, and put the power to base b of m. Let's suppose we didn't know what this was, and let's say that we're just going to call it x for now because we don't know what it is. It's x. So what is x in this particular case? Okay, so let's look at this as an exponential. B is positive, not equal to 1, so it satisfies the definition, and then I have it to a power. Okay, so I'm just going to write it in log format. Okay, so how does the definition go? So if I go from exponential to log form, then it has to be the log of the x to base b, and that's supposed to equal to then to the exponent, which is log of m to base b. Okay, so I have log of x to base b is equal to the log of m to base b. So what do you think the relationship is between x and m? Okay, it's kind of like I have as with exponential. See, if I have 2 to the 3 is equal to 2 to the x. What do I know about 3 and x? Well, they have to be the same number, right? They have to be equal. Yeah. If this x is anything other than 3, this is not going to be equal. This will be a contradiction. Okay, can't have that. Okay, well, it's the same thing here. If I say, okay, I have the log of, say, 2 to base 10 is equal to the log of some number to base 10, and I say those are equal. What's going to be the relationship between the x and the 2? Well, they have to be the same number. Otherwise, it's not going to work out. Those have to be equal. So that's why in this particular case, then, b to this power is x. Okay, and we see that x then over here by this, x has to be m. Okay. So I'm just kind of verifying the property. So this is saying then if you have b to a power, and the power is a logarithm of some number m to base b, in other words, this base here and the base of the logarithm is the same, then the answer is going to be whatever this expression is right there. In this case, it's m. Okay, clear this. The next one should be clear. Log of b to base r, log of b to the r power to base b is equal to r. That should be clear because it's saying b to the r equals to b to what power? Well, it's got to be r. Okay, so again, this is saying if you have the log of some base, and this base of the log is the same, and the answer is going to be whatever the exponent is. Okay. Number 5, you have, whenever you have the log of a product of two numbers, that's the same thing as the sum of the logs. So notice the way it works out. Log of m times n is equal to log of m to base b plus log of n to base b. And notice this works both ways. So this is saying basically that if you have the log of a product, you can write it as the sum of the two logs, and it goes backwards. If you have the sum of two logs, you can write it as a product. Number 6 states if you have the log of a fraction to some base b, then that'll be the difference of the log of the numerator and the log of the denominator to those same bases. And this again works backwards also. If you have the difference of two logs, you can write it as the log of a fraction. Okay. Number 7 says if you have the log of some number to a power r to some base b, then this power can become a coefficient. Okay. Notice what it is. The power here becomes a coefficient, and it goes backwards. If you have a log with a coefficient, you can rewrite it as a exponent. Okay, going back the other way. Now I do want to point out here that when you have the log, okay, base b of x to the r, okay, we just write it that way, then that's the same thing as the log of x and then to the base b, and I do it this way. Okay. Now I want to point out to you that if you have the log to base b, again some number x, and say I put the power here. Okay. Keep in mind this is not the same thing as the log of x to the r base b. Okay. They're different. Okay. This one here with the parentheses, you're computing the log of some number x to base b, and then you're taking that number to the r power, whatever that turns out to be. On the right side, here you're computing this out first. You're taking x to the r power, okay, x to the r power, and then you're computing the log of that to base b. And in general, these are not going to be the same number. Okay, so keep that in mind. These are different here. Okay, so those are your properties. Quick look at the properties. Okay. And in the next exercises that I have here, we'll be using these properties. Okay, so let me clear this. Okay, so this one, the first one says write as a single log. Write as a single log. So I have 2 log x plus log y minus 3 log of w. And remember, I don't have the base indicated, so that's understood to be base 10. Okay, so basically I'm going to use these properties that I have here. Okay, so I have a property for a sum. I have a property for a difference of logs. But notice the coefficients for these are either a 1 or a minus 1. Okay, so I'm going to rewrite this one. So I'm going to say this is the log. And again, let me clear this. I'm going to rewrite this and say this is the log of x to the second, plus the log of y minus the log, and I'm going to rewrite the third one as, so I'm taking the 3, I'm taking the 3 and putting it here as an x power. So I'm using these properties right here. So I'm actually using Actually, I'm going to use in this one, I'm going to use property 4, property 5, and property 6. Actually, more like property 7, yeah. So it's going to be properties 5, 6, and 7 that I'm going to use. Okay, so by putting this power here, where on the x is 2, I'm actually using property number 7. Okay, and the same thing if I put the 3 here. Now keep in mind that I could make this a plus and make this a negative here. Okay, I want to do it that way. But normally I don't want to mess with negative power, so I could make this a plus and a negative, but I'll leave the minus here and the 3 goes over here. Okay, so the instructions write as a single log. Okay, so now I'm using the properties. Number 5 states anywhere I have a sum of 2 logs, I can write it as the log of a product. Number 6 states anywhere I have a difference of 2 logs, I can write it as a log of a fraction. Okay, so the first two I can rewrite this way. So this can be written as a log of x squared times y. And just to emphasize that this is the log of this product, there's no confusion. I'll put this in parentheses like that. Minus the log of w to the third. Okay, so again, now I have it. I went from 3 logs to 2 logs, so I want one single log. So now property number 6 tells me any place I have a difference of 2 logs, I can write it as a log of a fraction. Okay, so these two can be written as the log. Then this becomes the numerator and this becomes the denominator. So this will be x squared y over w to the third. Okay, and just to make sure that there's no confusion, I'll put parentheses so it's the log of that whole thing. Okay. Now, I do want to point out to you that in some cases they'll give you a problem like this, and they'll give you sum or difference of logs, and they'll say write it as a single log. Okay. And sometimes they'll give you a single log and tell you to expand it into a sum or difference of logs. So in other words, it would just be working this problem backwards. So if I give you this right here and say expand this into a sum or difference of logs, and what you would do is say, okay, I have the log of a fraction, so that means I can write that as the log of the numerator minus the log of the denominator, and I would get this, and then I would look at this one right here and say, okay, here I have the log of a product, so I can write it as a sum of 2 logs. So this would go to that, and then this would be this. Okay, and then if I want to put the power, rewrite it with the powers here, I can write the 3 here, the 2 here, and wind up with what I started off with. Okay, so it came back to the same answer. Okay, let's clear this. Okay, in the next two, I'm actually going to be using property number 3. And notice property number 3 states if I have, again, a base b taken to a power where I have a log, and the base on the log is the same as the base here, then the answer is going to be whatever this is. Okay. And then if I'm going to be using also number 7, if I have the log of some number m to the r power. Let's see, make sure. Or actually number 4. If I have a log of b to some power, and these two bases are the same, then the answer is going to be whatever the exponent is. Okay, so okay. Now, if I didn't have the 2 right here, since this is a 3 and this is a 3, these bases are the same, the answer would be x. That would be it. Okay, but in the property there's no coefficient here, or the coefficient is 1. Okay, so in this case then I have to use a property first. Okay, so I would rewrite this as the log. Okay, and then this coefficient then becomes a power to this base right here. So this would be 3 to the x, and that would be taken to the second power. Okay. Okay, so let me rewrite this. That this would be the log base 3. Okay, power to a power here, multiply the exponent, so this would be 3 to the 2x. 2 times x is 2x. Okay, now the coefficient here is 1, and this base 3 is the same as this base right there. So those are the same, so according to the property, the answer should be the same as whatever the exponent on this base is, which in this case is 2x. So this becomes a 2x. And that's your answer. Okay. Clear this. Okay. Number 3, in this section here, states if I didn't have this 2 here, this base, I have a base taken to a power where the power has a log. So I didn't have the 2 right here, 7 and 7, the answer would be 5. Okay, so what I have to do then is, again, using the properties of logs, I can take this 2 and put it as a exponent. So this will become the log of base 7 of 5 to the second. Okay, but 5 to the second is 25. Okay, so now I have the base 7 and the base 7, and the coefficient here is a 1. So now I have it set up according to the property. So now you can see that the answer is going to be 25. 5 squared is 25. And that's your solution. Okay. So go ahead and review these properties and definitions, and I'll be back a few days or so with a video with more complicated. I looked at some very basic equations of logs and exponentials in this one, but in the next video we'll look at some more detailed, more complicated equations. And again, as usual, I'll put a link to the other channel in case you want to look at those. So we'll see you in the next video. Thanks for watching.